Very good morning to everyone. So we will be starting with the third lecture in our lecture series on perturbation theory of eigenvalues of matrices. So we recall what did we do yesterday. So in very few words, we will because what we had done. So we were looking at inequalities between eigenvalues and in terms of the operator norm of the difference of the operator norm of the matrices. So norm A in terms of norm A minus B, we looked at the distance between the eigenvalues. Now, when we saw that if our matrices are Hermitian or skew Hermitian, we have a way to order them. But when they are unitary, in general, we do not have any way to order them. In that case, now one important metric that we introduced yesterday, we will be actually looking at that now in today also, and we'll be using it extensively, in fact. So that is the optimal matching distance. So if you've forgotten, just to recall, that is minimum over all permutations on Sn, maximum over J, mod lambda J minus mu J. And and we showed that for Hermitian, skew Hermitian, or unitary matrices, we have d of lambda A, lambda B less than equal to norm A minus B. Recall lambda A is the multiset, so unordered tuple of n eigenvalues of A. Now the question becomes that, okay, we have seen three classes of matrices. What about the other? So what about the other case? What is the more general thing? What about normal matrices in general? For unitary emission, skew emission, it's all true. So is it true for all the matrices, all normal matrices? Now, this is unfortunately or fortunately, you'll say it's not the case. We don't have, so one can see now if you will take V, so there's something for you to just verify. Just look at this, no, you can note down this example, though it's there in the book on matrix analysis also. So you can, and we can see that my U is a unitary matrix. One can actually easily check it because my V is a unit vector, and then my B, so A is naturally diagonal matrix, so it's normal. B, because it's the way we are defining B, it's also normal. Clearly, the eigenvalues of B are the negatives of the eigenvalues of A, and we can actually see this optimal matching distance between, we can calculate the optimal matching distance that turns out to be under root of 28 by 13. But when we look at norm A minus B, it will turn out to be root 27 by 13. That is clearly that inequality that we were seeking is not true even for the, see, 3 cross 3 normal matrices. It's not very high. It's not that when we increase our n, there is a problem. It's the problem just starts, or it's there even for 3 cross 3 normal matrix. I've not talked about 2 cross 2 normal matrix, but 3 cross 3 apparently is the problem is there. Now, what do we do then? So if I have just a minute. So if we have, so now here, what do we do? We again look at another metric. So optimal matching distance, that is not working at least. So we look at another distance. Now what is happening? So when we changed from a way of ordering, so we had Hermitian, skew Hermitian, we changed to optimal matching distance because we didn't have a way to order. So optimal matching distance was taking care of our problem of ordering. Just a minute, my camera is off.
Yes, your camera is off.
Okay. Yeah. That's fine.
Yes, now it is.
Huh. Okay, sorry. So now what we took care in optimal matching distance? The problem of ordering. Now here, but we were insisting on taking care of multiplicities. That's why we were taking the unordered tuples, or multi-sets. So we were taking care still of the multiplicities. We were having one-to-one correspondence between the eigenvalues irrespective of multiplicities. But now here we just ignored that also. So here we see that as soon as I ignore multiplicity, so therefore now from lambda A, I'm coming to sigma A. That is the set of eigenvalues. That is the spectrum of eigenvalues. And here I will define not on the unordered tuples, I will define the distance on the spectrum of the matrices. So for that, again, there is a forthcoming exercise in metric spaces. So take any two compact, non-empty compact subsets, L and M of C. So it's not necessary. It can be any topological space on any metric space. Basically, you can take. But we are just restricting ourselves to C. So let L and M be any non-empty compact subsets of C, and we define S of L comma M to be supremum of the distance between L and the set M, where supremum is taken over all points of my set L. So that is basically infimum over all M, distance between mod L minus M, and then taken supremum over all L in L. Now we define the Hausdorff metric on the space of all non-empty compact subsets of C to be H of L comma M to be maximum of SLM and SML. So now you see SLM is something it's not symmetric in terms of L and M. So SLM can be very well different from SML. So now what we are doing here in this case, so on my metric, the basic one condition that my metric should satisfy should be symmetric. So here, what basically I am having is that I'm now my Hausdorff metric, I'm making it to be symmetric. So it's a nice metric. So here you see, I'm not defining from the distance between two functions. I'm not defining distance between points. I'm not defining distance between sequences or tuples, but I'm defining distance over sets here. So this is, in fact, this is called the hyperspace topology. So it is now an exercise. This Hausdorff metric, what we're defining, this H, is actually a metric on the space of all non-empty compact subsets of C. Also, one can see that, so it will be easy to verify. Again, you can put it in the exercise. After talking about this, we'll see this, we'll spend a little more minutes, few more minutes on this Hausdorff metric. So one can see that H of sigma A sigma B is less than equal to d lambda A lambda B. So see, the optimal matching distance is having the distance between the multisets or unordered tuples. And Hausdorff metric is basically giving the distance between sets. So the two things are different, but we have this inequality is always true at sigma A, sigma B less than equal to d lambda A lambda B. You can verify that. I will show you with this, give you an idea by giving some examples. Just two simple examples. Also, now this is again, so it's an again exercise, it's a simple exercise that for 2 x 2 matrices, my H sigma A sigma B is equal to d lambda A lambda B. So now as soon as I give you the next result, you will see that why the counter example where the inequality doesn't hold true for normal matrices was given by 3 cross 3 matrices, not 2 cross 2 matrices. Why? Because of this theorem. So now a theorem tells me that my H sigma A sigma phi for A and B normal, my H sigma A sigma B is less than equal to norm A minus B. And because of the previous exercise, I know that H sigma A sigma B for A and B 2 cross 2 matrices is equal to D lambda A lambda B. So therefore, for 2 cross 2 normal matrices, D lambda A lambda B is less than equal to norm A minus B. So the problem really starts at the level of 3 cross 3 normal matrices. And it starts there and it's there. But, okay, optimal matching distance, it's not true, but with the Hausdorff metric, it's true. So just naively, just roughly understand that here we are even ignoring the multiplicities of the eigenvalue. So now my sigma A, sigma B can be two sets of very different cardinality also. So I'll give you just two simple examples, just to give it, just to have more feeling. Before giving the proof of this, I'll give you some just two simple examples where you will have a feeling that okay, how is my d lambda A lambda B different from H sigma A sigma B? Okay, so basically it will be just I will talking about. So now let's have that my lands, there are two matrices, any matrices. I'm not interested in the what is the matrix exactly. I'm interested in what is the set of eigenvalues, because I will be just showing you how d lambda A lambda B and S sigma A sigma B can differ. So let's have that lambda A is the eigenvalue, is the ordered unordered pair. Let's say 1, 3, 3. Is it visible? And lambda B is 0, 1, 3. Then what is sigma A? Sigma A becomes 1, 3, the set, and sigma B becomes 0, 1, 3. Yes. So now sigma, so the two cardinalities can be different in sigma and sigma B. What is the distance now here? What exactly? So it will also tell me that first of all, let's take what is d lambda A lambda B. That is, we have more experience with it. So we can, so can you guess? So now we're, so these are real eigenvalues. So what will be, so what will be, just arrange them in decreasing order, then check it out. We will also come to it in this lecture later on also. But roughly you can see that this 0, 1, 3 and 1, 1, 3, 1, 3, 3. This will have distance 2. We can check it out. Okay. Now let's come to H sigma A sigma B. What it is telling me. So that is that I'll have when once we do this example, we will have at least a better idea of how this Hausdorff metric is calculated. So look at this Hausdorff metric. So what is the definition of Hausdorff metric? So I'm looking at H sigma A sigma B. Okay, so that is maximum of, then it is the, so the supremum of lambda in sigma A, distance between lambda, so distance between lambda and sigma B, and supremum of mu in sigma B, distance between mu and sigma A. So what is exactly telling me? If my H sigma A sigma B is less than equal to R, So that means all these are maximum supremum. So that means that everything here, so distance between lambda and sigma b is less than equal to r for every lambda in sigma a, and distance between mu and sigma a is less than equal to r for every mu and sigma b. What does it mean by that? Take any lambda in sigma a. So now what was the our sigma a? A sigma a was 133. So take any lambda in sigma a. Take 1. Now what is the distance between what is the distance between 1 and sigma b? 1 and sigma b is 0. Then what? Take 3. What is the distance between 1? What is the distance between 3 and sigma b? That is 0. Then take sigma b. Sigma b is 0, 1, 3. What is the distance between 0 and sigma a? It's 1. What is the distance between 1 and sigma a? It's 0. The distance between 3 and sigma a is 0. So now just you're taking distance of each point with the other set and taking the maximum. Because we are working with here finite sets, my spectrum or matrices is always finite. I don't have any issues. It's easy to see here in this, at least for the finite sets. So then what is a simple algorithm to calculate in our case, in our context, the Hausdorff metric? Just pick up one set, take every element of that set, and take the distance of that element with the other set. Write those points, then do the same thing with the other set, and then you'll get some finite number of values. Take the maximum of those values. That is the Hausdorff metric between sigma a and sigma b. That is the simple here thing here. So now in our case, at sigma a, sigma b is equal to 1. So therefore, so now here you see that, in fact, this I took an example because it will also tell me that how to have just to calculate just to get an idea how we calculate the Hausdorff metric. But now see, if I take even simpler example, I take lambda a to be 133 and lambda b to be 113. Then sigma a and sigma b are both the same sets. So h sigma a sigma b will be 0. But clearly lambda a and lambda b, the distance between lambda a and lambda b will not be 0. So that gives me that clear difference between my h sigma a sigma b and d lambda a lambda. So this we have got idea by using examples. I want you to exactly prove that out that h sigma a sigma b is less than equal to d lambda a lambda b and so on. Okay, but so now we come to the proof of our result. So what was our result? H sigma a sigma b is less than equal to norm a minus b. What will I show? So it's H sigma a sigma b is maximum of S sigma a sigma b and S sigma b sigma a. So what I do is, I'll show that. So now this is we prove that S sigma a sigma b is less than equal to norm a minus b. Then I can reverse a and b and I will have S sigma b sigma a less than equal to norm b minus a, that is norm a minus b. That's same. So I just need to prove this thing. S sigma a sigma b is less than equal to norm a minus b. Now what do I do here? What is S sigma a sigma b? S sigma a sigma b is supremum of lambda in sigma a, distance between lambda and sigma b. Okay, so that means if I want to prove this, so let's take norm a minus b to be epsilon. Okay, so norm a minus b, So norm A minus B is epsilon. So then let's right, because we should not, so just to avoid writing norm A minus B again and again. So we take norm A minus B to be epsilon. Now, what are we have? What do we look for? That for every lambda in sigma A, there is an element in sigma B. There is a mu in sigma B such that mod lambda minus mu is less than equal to epsilon. Then only my S sigma A sigma B. So that means that for every lambda, so let lambda belongs to sigma A. We need to show the distance between, distance lambda A, lambda time with sigma B is less than equal to epsilon. Sigma B is a finite set. So therefore, that means I have to show that there exists a mu in sigma B such that mod mu minus lambda is less than equal to epsilon. Now let us assume that this is not the case. So first of all, by translating both A and B, so by translating translate by lambda. So if A is normal, A minus lambda will also be normal and B minus lambda will also be normal. And norm A minus B will be same as norm A minus A minus lambda, and no, the distance between norm A minus lambda and B minus lambda. So now I can translate by translating A and B. We can assume that my lambda is equal to 0. That is something that's, I can do that, but it will make my proof very simple. So my lambda is equal to 0. First of all, I'm taking that my lambda is 0. And suppose for every mu belong to sigma B, so I'm going by contradiction. Mod lambda minus mu, that is mod mu is strictly greater than epsilon. It's not less than, so for every mu, mod mu is greater than epsilon. So I'm going by contradiction. Then what happens? Now look at B is normal. This will imply, so now for every mu in sigma B, mod mu is greater than epsilon. What does that imply? My B is also, so my B is invertible. Yes, because any matrix is invertible if and only if it does not have 0 as its eigenvalue. So B is invertible, B is normal, B is invertible, B inverse I can talk of. Will B inverse be also normal? Yes. B inverse, B is normal, therefore B inverse is normal. B inverse is normal, so B inverse is normal. And for normal matrix, and what will be the eigenvalues of B inverse? Eigenvalues of B inverse are, so B inverse is normal. What will be sigma of B inverse? Sigma of B inverse, what is sigma of B inverse? Sigma of B inverse is 1 by mu, where mu belong to sigma B. And so B is normal, therefore norm B inverse will be, so when yesterday we noted that if a matrix is normal, then its operator norm is equal to the maximum of mod lambda, where lambda is an eigenvalue of A. So maximum mod lambda, where lambda varies over spectrum of A. So here norm B inverse will be maximum of 1 by mod mu, where mu belongs to sigma B. So that will be 1 by minimum of mod mu, where mu belongs to sigma B. So mu belongs to sigma B. And this is, what is this? Mod mu is greater than epsilon. So for every mu in sigma b. So this is less than 1 by epsilon. So norm B inverse is less than 1 by epsilon. Now look at the matrix norm. So the norm of the matrix B inverse A minus B. This norm is less than or equal to norm B inverse norm A minus B. Norm A minus B is equal to epsilon. Norm B inverse is strictly less than 1 by epsilon. So this is less than 1. We know that if norm A is less than 1, then my I minus A. So now I have a result that if norm X is strictly less than 1, then something that we have, you would have at least seen similar things for numbers. So if mod X is norm X is strictly less than 1, then my matrix I minus X is invertible. So this will give me that my B inverse A minus B plus I is invertible. Is invertible. What is B inverse A minus B plus I? So just open up B inverse A plus minus identity plus identity. So this implies my B inverse A is invertible. And if B inverse A is invertible, then my A is invertible. Can A be invertible? Remember, we took that lambda is equal to 0 belongs to sigma A. A matrix is invertible if and only if it does not have a 0 eigenvalue. But A has 0 eigenvalue, therefore this is a contradiction. As 0 belongs to sigma A. And therefore I should have the now my assumption that I started with. So there should be some mu in sigma B such that mod mu is less than or equal to epsilon, and therefore my S of sigma A sigma B is less than or equal to epsilon, and similarly my S of sigma B sigma A is less than or equal to epsilon, and I'm done. Now here in this proof, if you would have noticed, I have just used normality of B. I have not used that A is normal. Nowhere I have used that the matrix A is normal. So basically, when I am talking about that S sigma A sigma B is less than or equal to norm A minus B, I just want B to be normal. A can be any matrix. So this is the difference. But because I want in H sigma A sigma B, both S sigma A sigma B and S sigma B sigma A, therefore I need both of the matrix finally to be normal for this theorem. So now we have this thing. So, and for 2 cross 2 matrices, because these are the same thing, therefore we have the other thing also. Now see, so at least I can see that for operator norm, because I have a counter example, it's clearly not true. So now for a long time, because these were true for 2 cross 2 normal matrices, these were true for this inequality d sigma, d lambda a lambda b was less than or equal to norm a minus b for unitary matrices, Hermitians, Q Hermitian, or so for a long time, many great mathematicians were expecting that it will be true for normal matrices also. Finding the counter example was also not an easy task. You will see that not many examples, counter examples for that inequality that we have. In fact, we don't have many counter examples. The first counter example was given by John Holbrook in around 1990s, and so that was through MATLAB. So it's not an easy task even to get a counter example here. So for a long time, so Hoffman and Whelan, great mathematicians, were trying to prove the inequality for the operator norm. Obviously, for operator norm, the inequality is not true. But what they got was nice, beautiful inequality for the Frobenius norm. So this is a very well-known result known as the Hoffman-Wieland theorem. And what does this say? That now see, you'll see that as soon as I change the norm on the matrices, I change the distance on the eigenvalues. My Frobenius norm corresponds to the Euclidean norm. My operator norm was corresponding to something like the supremum norm. Operator norm, because it's supremum of norm AS. So there I was talking of the supremum metric. Just a minute. So my screen has been stopped. Just
Yeah, screen may have to again.
yes. So just. Yeah, that's why. So now, as soon as we change the the norm on matrices, we correspondingly change. Now here, my Frobenius norm corresponds to the Euclidean norm. So there, though I am looking at the optimal matching distance because I clearly do not have a way to order them. So I am looking at the minimum over the permutations. The thing I have. But now instead of like looking at maximum over all j's mod lambda j minus mu j, I'm looking at the so my thing becomes now the Euclidean norm. So mod alpha j minus beta j whole square over 1 by 2 lambda j minus mu j. So that I am considering here. Now, the Hoffman-Wieland theorem tells me that if I take the minimum over all permutations, the Euclidean norm of between lambda and mu sigma mu sigma mu tau, then I have it's less than equal to, and if I take the maximum over all permutations, my norm A minus BF is less than equal to the maximum over all permutations. We will see that can go in one go, in fact, in this case. So what the inequalities? One thing also we see that, for example, if I have only Hermitian matrices, then what we were doing for only Hermitian matrices, I was saying that okay, put this in the increasing order, put in the decreasing order. In now for this Hoffman-Wieland theorem, if I have one matrix to be Hermitian and the other matrix to be any arbitrary normal matrix. So in that case, eigenvalues of Hermitian matrix I can order, and then of the other matrix I can order as per the real parts of the eigenvalues of B. So because of this inequality, so because of this, now again, so because of this inequality, I can actually talk about I can order them. Now, one thing that I want you to, this is simple thing that you can, so because if I have some x minus y plus iz square, what is that? That is x minus y square plus z square. And therefore I have the thing. So now see, and now I'm having Euclidean norm. So that is will be summation of x minus y square plus z square. So xi minus yi square plus zi square. Now I want you to think, okay, I am saying that if B is normal, any arbitrary normal, you order it as the according to the real parts of the eigenvalues. What happens when B is skew Hermitian? So if you have, you can write the answer out, in fact. So what happens if B is skew Hermitian? Can you suggest me some ordering of it? Or is there, so what do you think? If A is Hermitian and B is skew Hermitian, what happens? Think of it. Okay. So we'll now start looking at the proof. Again, this takes us to some very beautiful notion in matrix theory and in convex analysis. So we look at what we call as a doubly stochastic matrix. It's also related to majorization theory and inequalities, but I will not be going into the details of it. I will be just introducing what is necessary for our proof. So what is a doubly stochastic n cross n doubly stochastic matrix? S is n cross n doubly stochastic matrix. So all entries will be greater than or equal to 0. So they obviously will be real numbers, non-negative real numbers there will be. And the sum of every row and the sum of every column adds up to 1. So if I take summation over I, Sij, that will be 1. Summation over j, Sij, that will be 1. So sum of every row and sum of the entries of every row, sum of entries of every column is 1. So that is a doubly stochastic matrix. Now one can see that it's simple to see that this forms. So my matrices are really subsets of Cn square. Now, in this case, they are subset of Rn square anyways. And I know that any subset of Rn square is compact if and only if it is closed and bounded. One can easily check again here that because of this thing that all row sums and all column sums are equal to 1, I have that this set is the set of all doubly stochastic matrices is bounded. Just go with the normal Rn square, the metric on Rn square, what you will think, and you can show that it's closed. So it's a compact set, the set of all doubly stochastic matrices. Oh, so so it's a doubly and also so it's a convex set. That means that if I take S and T to be two doubly stochastic matrices, then and I'll run my T to be anything between 0 and 1, then 1 minus Ts plus small t times capital T will again be doubly stochastic. So you don't know what happens. Again and again. So it's a compact convex set, and it will every compact convex set. So and is a so it has extreme points. So every element in compact convex set is a linear combination of its extreme points. What are the extreme points? So now see, we take what we call a permutation matrix. This is a matrix which has exactly one entry in each column and in each row. There is exactly one entry which is 1 and all other entries are 0. So clearly this is a doubly stochastic matrix. And so now why we call this as a permutation matrix? This because this is a one-to-one correspondence with permutations on the Z1 to N. How? If I take any permutation tau we can take the p tau as pij to be 1 if j is equal to tau I and 0 otherwise. P tau of x is nothing but the just I'm promoting the coordinates of x. So p tau x is nothing but x tau 1 till x tau 1. So, and these are, at least I can see that these are the extreme points of doubly stochastic matrices. So, what is an extreme point? Extreme point of a convex set. So, B is an extreme point of DSM. Why? Because it cannot be written as a strict convex combination of two other points of DSM. So my P cannot be written as 1 minus TS plus TT, where S is not equal to T. And S and T are in DSM. So therefore, it's called an extreme point. And a nice, but I won't be going into this. So take on faith that, so Virchow's theorem, and that in fact uses the matching lemma that we did yesterday. So Virchow's theorem tells me that permutation matrices are the only extreme points of set of doubly stochastic matrices. So that is a very beautiful result and a very important one. So identifying the extreme points of compact convex set is not always that simple. So it's not a simple result. It's not. It's a very beautiful result and a fundamental result. So permutation matrices are the only extreme points of the. So every doubly stochastic matrix can be written as, in fact, the convex combination of permutation matrices. Now coming to convex analysis. Any convex function will have its maximum on DSN. So if it does. So it says that any convex function on DSN will have maximum attained at the permutation matrix. In particular, if I take affine map, its minimum and maximum will be attained at some permutation matrices. That is the important result actually that we will be using. So any affine function, any real affine function has its maximum and minimum attained at permutation matrices. Now we will come to the proof of Hoffman-Wieland result. Okay. So what we have? We have two normal matrices A and B. Now we come to, in fact, we mentioned yesterday spectral theorem. So A is normal. Therefore, I can write A as U D1 U star, where U is unitary, D1 is diagonal. B I can write as V D2 V star, because A and B are both normal. Then what is norm? A minus B F. So remember, so norm A minus B F. So remember, this will be the square root of trace A minus B star A minus B. Okay. Now, by just, so you know that trace of xy is trace yx. By using this kind of thing, and so we can show that norm A minus BF. So first I will have just, so norm A minus BF square. Let's have that. That is equal to norm, and put the value, the expression for A and B. U D1 U star minus V D2 V star F square. That is now A. So now this you can verify by just using trace xy is trace yx and doing some calculations. So here then I can show that this is equal to, so just I'm now taking out U outside. So D1 U star And from the right hand side, I will take V star outside. So it's V minus, so here I will have U star V D2 V star. I've just taken out U and V, U from the left, and V star from the right. So now by using the definition of Hermite, this is a square root of trace. So norm a minus b f whole square, that or norm x have norm Frobenius norm of x square is trace x star x. You can show that this is in fact, because u and v are unitary, therefore this is equal to norm d1 u star v minus u star v d2. U and V are unitary. So product, so U star is also unitary and U star V is also unitary. So let W is equal to U star V. So W is a unitary matrix. Let's take, so W tilde to be the matrix with the ijth entry as mod Wij square. It is a matrix with non-negative entries because it's mod Wij square. And what is the sum? What is the row sum and column sum? What is summation mod Wij square summation over I, and what is summation mod Wij square summation over j? So for a unitary matrix, the sum of the square, so all the rows and all the columns are unit vectors. So this is, both of them are equal to 1. So my W tilde is a W stochastic matrix. So now I do the thing. So what I have, my norm A minus BF square turns out to be norm D1 W minus W D2 norm F square. This I can write as, so what will be the values? So if D1 is diagonal alpha 1 till alpha n, D2 is diagonal beta 1 till beta n, these are the eigenvalues of A and B, then what is D1W minus WD2? What is the ijth entry of this matrix? This matrix will have eigenvalue, ijth entry as, the ijth entry would be alpha I minus beta j Wij. You can, it's just a simple matrix calculation. And in fact, very simple because D1 and D2 are diagonals. So alpha I minus beta j Wij. So then I know that the Frobenius norm square is nothing but the sum of the modulus square of all the entries. So norm A minus BF square turns out to be summation over Ij mod alpha I minus beta j square mod Wij square. Yes? Now what is this? So here I get a mapping. Let's say phi from DSN, the set of all W stochastic n cross n matrices, to R as phi of S, so is equal to summation over Ij mod alpha I minus beta j square Sij. Because mod Wij square is a W stochastic, is the ijth entry of W stochastic matrix. So this function now, where will it have the maximum and the minimum? This is an affine function. So this will have maximum and minimum attained at the extreme points, that are the permutation matrices. And therefore, now because of this, there exist the maximum and minimum of phi are attained at some permutation matrices, and permutation matrices correspond to the permutations, the p tau 1, p tau 2s, let's say. So then what we're having? In p tau 1, only I comma tau I element is 1, otherwise for every I, otherwise all are 0. So this means that the minimum there is attained that so the minimum, so my norm A minus BF square is a value on phi. So my phi of this W tilde is greater than or equal to phi of P tau 1, and phi of W tilde is less than or equal to phi of P tau 2. And therefore, what I have? The minimum, so my summation mod alpha I minus beta tau 1 I square is less than equal to norm A minus B F square is less than equal to summation over I mod alpha I minus beta tau 2 I square. And that is, we are done. So simple use of W stochastic matrices and Werkhoff's theorem, that the extreme points are permutation matrices. That's an important point in this case. So now that's the one result that we will be doing here for Frobenius norm. Now see, in this, so we know so that the Frobenius norm, so operator norm is less of any matrix X is less than equal to the Frobenius norm of the matrix, and Frobenius norm is less than equal to the square root of n times the operator norm of the matrix. That is something like that you have this the maximum norm in Cn and the maximum norm in Cn and the Euclidean norm in Cn, because just take for normal matrices. So my number for a normal matrix A, my Frobenius norm is summation mod lambda I square over 1 by 2. That is the Euclidean norm of lambda i's. And the operator norm is maximum of mod lambda I. That is the supremum norm. So here, this really corresponding to the Euclidean norm and the maximum norm on Cn. So therefore, we have this inequality that norm of A is less than equal to norm A, the Frobenius norm of A, and this is less than equal to square root of n, where n is the dimension of the matrix times operator norm. And directly from here, we get that my this d lambda A lambda B will be less than equal to square root of n times norm of the operator norm of A minus B. Remember, we just saw the counter example that that d lambda A lambda B is not in general less than equal to norm A minus B. I didn't say that there will be any inequality. Will there be not? I didn't say that. But now, because of the Hoffmann-Whelan theorem, as a corollary of Hoffmann-Whelan and the relationship between the two norms, the Frobenius and the operator norm, I know that I have some inequality, but the factor is square root n. So now this is dependent on the dimension of the matrix, the order of the matrix. If it is n cross n, so if it is 10 cross 10, it's square root 10. If it is 1 million cross, it's a square root million. So it's growing. The question is, can we have a constant which is independent of the dimension? Can we have now a constant, in fact, which is not dependent on A, B, or the dimension of A and B? Can we have such a thing? Yes. And this is, in fact, beyond the scope of our course. So this is a beautiful theory. The interesting thing, so now one can actually have that there is a universal constant C such that d lambda a lambda b for a and b n cross n normal matrices. So it's independent of A, independent of B, independent of the dimension of A and B. So d lambda a lambda b is less than equal to C times norm A minus B. And so, an unpublished work of Courses showed that, in fact, that C will be less than pi. The interesting thing is now here, and there is something who is more interested, can actually go to matrix analysis and look at the sixth chapter. So here, this is an equality that I'm talking about on eigenvalues. Now, a similar problem I can talk about that, okay, if A and B are close enough, how close are their eigenvectors or eigenspaces? And that is a more difficult problem. But this inequality that we are seeing here, it actually comes as a consequence of the work of Bhatia Davis, McIntosh, Davis, Kahan on the eigenspaces, the perturbation of eigenspaces. So this you can say in quote that it's a roundabout way. Eigenvalues look to be more tractable. But vectors, as soon as from one dimension I go to n dimensions, it becomes less and less tractable. So here I'm going to a roundabout way, looking at a more complicated problem, and then coming back to the easier looking problem and getting a result on that. So somebody who's interested can actually try to see that if you can get something just working on eigenvalues, if you can have a simpler proof to this inequality. The other thing is C, the exact value of C is not known. It's just that there is another constant C2 that they call coming from the variation of spectral subspaces, that it will be less than C2. One can say that it's less than pi, but exactly what will be the best constant factor here, that is also not known. So if somebody interested, they can really look at it. Okay. So now, so here we come to, so what happens when I've talked about normal matrices, I've talked about Frobenius norm of normal matrices, operator norm. Now I come to what happens when the arbitrary matrix is there. So here we will stop. We will continue for the arbitrary matrices in our coming lecture at 1 o'clock. So, we will see that what can we really get here. So now my matrices won't be even normal. Then what I get. So here it's a reminder for you where we started, that the eigenvalues in general are not even continuous. So I should not be optimistic. Obviously, I cannot talk of the distance or so and so. So then for arbitrary matrices, we will be looking more at the now continuity of eigenvalues.